Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This video and the others in the Chapter 6 Problem Solving with Python playlist are an introduction to the concepts you will need to write programs with lists. This video accompanies Problem Solving with Python Chapter 6, but it's okay if you don't have the book. The videos stand alone as instruction on these topics. In the last video, we talked about lists and functions, passing lists as parameters to functions and returning lists from functions. In this video, we're going to look at different ways to structure a list to store related data, or records of data. Let's dive in. Many problems that we solve with a programming solution involve processing records of information. Rather than processing a list of numbers by itself, these problems require us to process numbers with additional context that we need to incorporate into the processing. Let's look at a couple of quick examples. This dataset is available on NASA's website, and it's called Leaf Chemistry 1992-1993 ACCP, and the description tells us that leaf samples were collected from different sites and analyzed for carbon and nitrogen content. Each record describes one sample that was collected and includes information such as a sample ID, the ID of the site where it was collected, the plot ID, a collection date, the species, and a lot of values resulting from chemical analyses such as cellulose, carbon, nitrogen, weight, etc. The information for each sample is related, and we must be able to link it in a program if we're going to answer any meaningful questions about the data, such as what is the average carbon content of a leaf by species. Now let's consider data that might be more personally meaningful, grades in a course. This is not real data, but it's an example of what my gradebook might look like at the end of a semester for an introductory programming course. Each row is a record. It's the grades for an individual student. Each column is a graded assignment. Obviously, I need to keep the rows together in order to advise my students and calculate their individual grades. But the column data is interesting too, because it allows me to answer questions about individual assignments, like what was the highest, lowest, average, and standard deviation of the grades. That helps me determine the quality of the assignment and student mastery of the concepts being assessed. Because processing of related data is so common, there are many different computational solutions available. For example, we could answer the questions I've raised and more complicated ones with a spreadsheet, a database, a specialized data analytics language like R, or library like Python's pandas. There are also specialized constructs within most languages for grouping data called classes or objects. We can also use lists to group data, and learning how to group data with lists will help you think about data and data processing in a way that is common to all of these solutions and will help you learn to work with them. Let's begin with parallel lists. Suppose we want to answer the question, what is the average percent of carbon by species over all of the samples? So the average percent of carbon in the American basswood leaves collected, the average percent of carbon in the white oak leaves collected, etc. To answer that, I'm going to represent only a subset of the data found in this data set, and I'm going to just represent a few records of values as an illustration of how to process parallel lists. Looking at how this data that I downloaded is organized, it's the same as the gradebook data I was showing you earlier. Each row is a record of related information, and each column is a category. These qualities are part of a format called tidy data, an idea conceived and originally described by Hadley Wickham. To move this data to parallel lists, the data in each column will be stored in a separate list. And the row then becomes the data stored at the same index in each list. So let me put this into Python. I'm just going to work in the main or global frame, and I'm only going to take the top 5 rows and the columns sample ID, species, and carbon. Each of these columns will be a list. The data types and ranges of values of these columns, by the way, are all documented on the website. So I know that sample ID and species are of type string, and carbon is a percentage with values ranging from 39.09 to 54.37, so a float. I'll just copy that data over to Python and come back. Okay, now compare the lists and the original table. At index 0 in each list, I have the values in the first row of the table. In sample IDs, at index 0, I have 92BHIS10BW1. In species IDs at index 0, I have TIAM, which is the code for American basswood. And in carbon at index 0, I have 47.13. In the table, we can see that these are the values in the first row. And if we continued to compare, we'd see that the values at index 1 are the values in the second row of data in the table, etc. The index is what relates the values when we have parallel lists. How do I process this to answer my question, what is the average % carbon by species? For the purpose of focusing on parallel list processing, let's further simplify this question to what is the average % of carbon for the white oak species with code QUAL. From the loop and list processing videos that describe variable roles, you might recognize that we'll want a variable in an accumulator role to add up the carbon percents for all the samples that are white oak. And we'll want a counter as well, so we know how many samples are of white oak, so we can divide by that value to take an average. So I'm going to add that loop, and we'll talk about how it works with parallel lists. Here is that code. And let's draw a picture, too, to illustrate how we process parallel lists. I've drawn the lists so that the parallel elements are aligned with each other vertically, and I've drawn in the indices of the lists. This helps show their relationship. Now, in the code, we're using the pattern for I in range length of the list, and I'm selecting one list, sample IDs. All lists should be the same length if we're working with parallel lists, and if they're not, we're going to get an error with this code. This code is focused on processing, not validating that the lists are the same length. We use the for I in range pattern because we'll need that index to access the related elements of a record. In the loop, we can use I to index into the lists, and that will give us each part of the record. So we first check if the record is a record for a white oak leaf with the code if species ID sub I equals qual, the code for white oak. And if so, we'll increment our counter and add carbon sub I to our total carbon variable, our accumulator. If we didn't have this parallel list structure, we wouldn't know if a carbon value belonged to a white oak or another species. It would just be a list of all carbon values. Once the loop is done, if we counted any white oak records, we calculate the average by dividing by count and report the result. If there were no white oak records, we print a message. So to summarize, to process data stored in parallel lists, we can iterate over the lists using an index and use the index to access each element of a record each time through the loop. The first time through the loop, when I is 0, we're accessing the record that is stored across lists at index 0. The second time through, I is 1, and we're accessing the record that is stored across lists at index 1, etc. Now let's look at a different way to use lists to store data, and that is to use a list as a record. Up until now, I have always used a list to store one kind of data. In our parallel lists example, 2 lists stored strings and 1 list stored floats, and each list stored data of the same type, not just data type. 1 list was sample IDs, 1 list was species IDs, and 1 list was carbon percentages. But an advantage to Python lists is they can hold different kinds of data in the same list. So returning to our original table, instead of putting columns each in their own list, we can put a row in its own list, and then put all of the rows into a list of all data. This program is called record lists.py, and I've drawn a picture of this data as well. The list consists of 5 sublists, and each sublist holds 3 values, a sample ID, a species ID, and a carbon reading. I've drawn the lists vertically rather than horizontally to emphasize the structure of the data, but you index into these sublists as usual. The first element, the sample ID, is at index 0, the species ID is at index 1, and the carbon reading is at index 2. You can see how this is defined in the code. We have the outer brackets for the outer list, and then each inner list is within, separated by commas, the same as you would do if we had a list of ints or floats or strings or bools. I've annotated this as list of string, float. And I've annotated and initialized some constants to make indexing into the sublists clearer. Sample ID is 0, the index of the sample ID. Species ID is 1, the index of the species ID, and carbon is 2, the index of carbon. That's within each sublist. Now, to answer our question about white oak carbon percentage, we'll iterate over the outer list by writing for leaf record in leaf data. Remember that if we iterate over a list using this pattern, the loop control variable, here it is called leaf record, takes on each value in the list. Each value in the list is one list of leaf data. So for example, the first time through this loop, leaf record is the list 92BHIS10BW1 TIAM 47.13. And I am using my constants to index into that sublist to make this code very clear. If leaf record subspecies ID equals qual, the ID for white oak, then total carbon plus equals leaf record subcarbon, and we accumulate into the total. The final part of the program is the same as before. We check that we're not going to divide by 0 and calculate and report the average carbon for white oak, or we report that there were no white oak records. So that is two ways that we can use lists to represent data that is more complicated than simply a list of homogeneous values. And this gives you some relatively straightforward patterns for processing data stored each way. I'm going to end this video here. I've included some auto-graded exercises in the description of this video so you can practice processing data stored each way. Once you've mastered the concepts here, you're ready to move on.